Tracking the path of a projectile or a moving observer often feels like juggling too many variables at once, usually ending in a mess of overlapping formulas. The solution is a strict dimensional split, breaking complex 2D paths into two independent straight-line motions. Whether it's a vertical drop along the y-axis or a horizontal slide along the x, these motions do not interfere. The only variable they share is time. Moving away from dense 2D formulas in favor of this split allows you to handle advanced scenarios where standard equations start to break down. Top left on this reference sheet, standard projectile motion breaks into components. Initial velocity resolves into ux and uy. Horizontal acceleration, ax, is strictly zero. Down in the basics box, the ground-level launch formulas for maximum height and time of flight rely entirely on that vertical uy component. Throwing a ball horizontally from a building changes the starting conditions. With zero initial vertical velocity, the standard ground-to-ground range formula fails. Instead, find the time of flight using the y-direction equation, square root of 2h over g. Then multiply by the horizontal x-velocity for total range. Treating the drop and forward throw as two distinct 1D problems prevents mistakes when the launch doesn't start and end at the same height. This logic also simplifies relative motion, shown here in the center of the notes. The core equation, VAB equals VA minus VB, means you stop the observer, reverse their velocity vector, and add it to the target. In case 2 in the top right, a runner moving horizontally at 4 meters per second through vertical rain creates a right triangle, making the rain appear to fall at a 45-degree angle relative to them. But visual intuition fails in case 4 at the bottom right. Here, rain falls at an angle, and the man sprints at 8 meters per second. Reversing his velocity and adding the rain's horizontal component yields a net relative velocity of exactly -4. Relying on this vector reversal, rather than guessing the visual tilt, is the only way to find the true angle of the rain. To consolidate this, we prioritize building our time, height, and range equations using ux and uy components instead of raw launch angles. We then pair those with the relative velocity rule, treating it as a consistent process of vector subtraction. This vector-based approach translates directly to circular motion, where we track how constant centripetal acceleration points toward the center at v squared over r. Mastering the independent axis rule gives you a repeatable method for solving motion, which is essential for the mechanics chapters that follow.